So, just a show of hands, how many people here have worked or just used MicroPython? We've got 2, 3. So I assume then not a lot of people have heard of or have used expressive ESP32 microcontrollers. We've got another 1 or 2. Okay, so hopefully this will be all new. Well, it will be all new, but hopefully a little bit interesting to use. So MicroPython, it started as a Kickstarter project, 2013, by Damien George. He's an Australian physicist. And his goal was to take Python 3 and run it on really constrained environments. So we're talking about environments that will have about 128K of ROM, 8K of RAM. It'll run on smaller environments, but I think if you want to do anything somewhat useful, that's the minimum type of requirements you need. These devices, low cost, small memory, small little processors, but you get REPL onto them. You get a small set of Python libraries you can interact with, and some of these microprocessors do have quite a lot of capability now for very, very minimal cost. I include here, there's a link to the download of the installation, and there's ports of MicroPython for quite a lot of different microprocessors. And if you don't have one of these little control boards, there's actually an online emulator where you can go and it'll play with it there and get a feel for it. And it's quite good. As I said, the presentation, I'm using Jupyter notebooks, and I've installed the remote MicroPython kernel on it. So I just put in a quick note on the installation there. It's relatively straightforward. So what do you get for your 10 euros, $10? So I've just thrown up a flavor of the types of devices. I'm using boards that are based on a processor called the ESP32. It's actually from a Chinese company. And they kind of got known in the West on the maker community in about 2014. They came out with this processor, the ESP8266. And it had a reasonable performance. It had about a dozen I/O pins on it. But the interesting part of it is it combined Wi-Fi on the one chip, and it cost $2 or $3. So the maker community really, really liked this. And then in about 2016, a bigger brother of that came along called the ESP32. And this here is the actual processor, this part at the top. So you got a system on a chip. You can see this up here is a PCB Wi-Fi antenna. The rest, and when you're looking at these boards, you'll find they all follow a similar format. They're all about like 2 centimeters wide, about 4 or 5 centimeters long. They expose out quite a lot of the pins, the I/O pins, out onto 2 rails along the side, and they'll have a micro USB connector at the bottom, and the connector provides power and also provides your way of interfacing into the board. And then this board on the left here costs about $5 on AliExpress or Banggood, and it's a similar type of board that I have here on this prop I have here. The board in the middle, a little bit more expensive, 9 or 10 euro mark. It has a bigger brother of the processor on there, so it has the ESP32 with about 8 megs of memory and about 8 megs of flash for storing your application on. It has an SD reader. It has battery connector here, so you can plug in a LiPo battery. It has a circuitry on there for charging the LiPo, and the ESP32 has some very good sleep management modes. So if you think about having an IoT device stuck in the middle of a field, it may wake up every 30 minutes, reading some data from a sensor, transmit it, go back to sleep. And so with a LiPo, you could be running that. For weeks or months with the deep sleep modes that are on these processors. The example at the end is an interesting one, about $15 mark. It's actually a developer kit that includes what's called a LoRa chip. LoRa stands for long range. So again, it has the ESP32, the chip is mounted on the back of the board. It also has a LoRa chip. So what it is you see a lot of IoT type applications, and the device is remote. So obviously you're out of range of Wi-Fi, you're more than 50 meters away, you may be like a kilometer away. You have a couple of options. LoRa, Sigfox are two very popular wireless options, or you connect it into the mobile network to LTE or some of those. So LoRa is designed to operate over several kilometers, really low data rates, like a couple of hundred bytes, kilobyte hour to 1 or 2 kilobyte data rates. And again, about $15. I've got some examples of these with me if you want to take a look at them afterwards. So let's see if we can go down here. So as I mentioned, there's a couple of different types of features on these at different price points. What is common on all of these is that unit at the top. I need a better mouse, so apologies here. That system at the top of all these boards is the ESP32. And at its core, it has a dual core processor here. That's running at up to 240 megahertz. It has two wireless capabilities. That's Wi-Fi 2.4 gigahertz. It doesn't have a 5 gigahertz capability, but just 2.4 gigahertz, and Bluetooth low energy as well. It's got built-in cryptography acceleration. It was one of the problems of the old processor. It was if you got access to that, you can get access to the code on it. So now they've put in quite a lot of cryptography acceleration in there to try and make them stronger. And then it's got a support for a plethora of common hardware interfaces. And I'll touch on some of these. So some of the most common one is I2 It's a 2-wire bus that's very common with sensors. SPI or SPI bus is it's connecting into use a lot on displays, reading SD cards, things with slightly higher data rates. So I2 good for maybe 100, 200 kilohertz or access. So if you want to access things in the megabytes, SPI is what's used. UART, so your serial interface. CAN, if you've got cars, they all run on a CAN bus, so you can interface into them. Temperature sensor, it's got capacitive touch sensors, analog to digital, digital to analog. So there's quite a lot of range of hardware capability in these little devices. And an interesting part of the ESP32 is this low coprocessor module. So what you can do is, if you're running all of this, a 240 megahertz processor, your Wi-Fi, it's power hungry. So what they've done is they've brought in a whole lot of various sleep options. So the only thing, you can power down different parts of this block, of this processor, and only have the ultra low power processor running. So that it's only pulling in very, very tiny amounts of power. But you can wake it up from a timer or from an interrupt from an external pin, and then start powering on the core processors or the Wi-Fi to do a bit of work. When it's done, go back to sleep. Okay, that's kind of a block diagram of what these ESP32s look like. Yeah, okay. Just one comment if you're buying these. So just go onto AliExpress or Banggood, you'll see these. Just type in ESP32. Just caveat, pick the ones that have been sold a lot or have a lot of reviews, because you'll find that there's schematics available for them. Some of the more obscure ones you won't find schematics for, so pin mapping it'd be hard to find out where the pins are assigned. And then if you're picking a device that has maybe a sensor on it or a display on it, pick one. You need to do a bit of research that they're a popular model, because getting Python libraries or MicroPython libraries for them can be a bit tricky. There's lots of C libraries, but only the popular models will be that will be ported to MicroPython. So just a word of advice if you're looking at these things. As I mentioned, I'm using I'm using an extension onto Jupyter Notebooks to remotely run the code on my little board here. So a few little demos here. So the first thing we need to do is connect. What I have here, if you can see this, is I have one of these developer boards here, and I have a little PCB I put together. It's got connected into some LEDs, and then some what are called NeoPixels. These are programmable LEDs that you can change the color and address them, do all funky sorts of patterns on it. And I've got an environmental sensor on here that just reads temperature, pressure, humidity. And there's a few other bits and pieces on here. So what's the Jupyter Notebook is just going to be talking directly to this, and all the code is going to be run on this processor directly. and it's using a web REPL for that. So the first thing to do here is obviously connect to the device, and hopefully we'll come, oh, as always, let's redo that. And we can edit that out of the video at the end. Okay. So we're now connected to the device. So one of the first little things we'll do is we'll have a look at what's there. So we import the system library, and we're just basically querying it to tell me it's an ESP32 platform and the version of MicroPython that I'm running there. There's a bunch of magic commands for this kernel. I'm not going to run it here, but it's mainly around connecting to the device, disconnecting, transferring files. So you can have a read of that. I throw it in there.
Do you have to look at what comport is?
Yeah. Yeah, so on the command there, you specify the data rate and the COM ports there.
You just use that device manager to see which one it's
Yeah, so you look in your device manager, see where the COM port's connected up. So this is USB. I have there's a particular driver I have that maps the COM port onto the USB into the COM port. But if you look at your ports list, and then in there you just specify the baud rate and the COM port. There's plenty of help online around that. So let's have a look at, so first place we'll have a look at here is modules. So these are the modules that are actually installed in this version of this port of MicroPython on this device, and they will vary slightly from the device you're doing. Since I'm running an ESP32, there's some hardware-specific devices here around the ESP32, and then you'll start seeing, names you're familiar with from the Python libraries prefixed with U for micro. So you'll have standard libraries like requests but this on a MicroPython, they cut them down because you've got a constraint environment here. You may only have a couple of 100 kilobytes, so they just put the core functionality into those libraries. And there is a plethora of libraries up there. At the top, there's a URL there where you can go and find libraries for, you name it, there probably is a library for it. But be mindful, it's a constrained environment. It's, the flash on this one has maybe 4 megs of flash, so you can fill it up pretty quickly if you start filling it up. So just be mindful of that. So these libraries over on the right, prefixed with the U, are basically MicroPython versions of kind of standard Python type libraries. And then you'll start seeing some unusually named ones, like NeoPixel. These are NeoPixels here, these devices. So there's a library to control them. You'll have DHT, that's a temperature sensor. But one of the most important ones is this library called Machine. So if we have a look at that. Now, so as I mentioned, when you saw that block diagram, on the left-hand side, there was a lot of different standard interfaces supported in this ESP32. And you can start seeing these names replicated in here. So you have your I2 square bus, you have your SPI interface, you have your serial interface, you have a plethora of them there. So the machine module is probably one of the first areas you're going to be looking at. Now, let's say these boards, again, they all follow a similar type of format here, the pins down the sides. This particular one is for this particular board here. It just shows you, I think it's got about 34 I/O pins, but the I/O pins are multifunctional. It's not so pin, like pin 32 here, it can be configured as a general purpose pin, so an input or an output. You can enable a pull-up resistor on it or not. It can do analog to digital conversion on the same pin, and it has a capacitive touch sensor on the pin. And then also inside on the device, you can attach interrupts, pulse width modulation control, and a bunch of other devices. So all the pins are generic. They're mapped through a matrix inside that you set up in your code. And this particular board, I think, has about 34 pins that you can program. And when you buy in your boards, that's what I say is check the schematics are available, because this pin mapping will vary manufacturer to manufacturer. They may not expose all 34. They may reserve some for certain types of device, for certain features, and it varies. So there's a list of the typical I/O that's on these here. Now, so the blinking LED is the kind of hello world of microcontrollers. So what I have here is a short little bit of code here. I have, on this board, I have two LEDs in the middle. They're wired up to pin, they go through a driver into pin 26. So the first line here specifies pin 26 as an output. And then I just have a loop that's going to turn it on for a second, turn it off for a second, and that's it. And just go through that loop 10 times. So let's quickly run that, and hopefully you'll see some blinking lights. Okay? As I say, it's a hollow world of MicroPython. So we have to start somewhere easy. So another way of controlling the LEDs is using pulse width modulation. So there we were turning a signal high, which is LED on, turning it low, LED off. Pulse width modulation is you set up a frequency, and then you basically say you can vary the duty cycle of how much is high. So you can say it's 50% high, so it's high for half the pulse, low for the other half of the pulse, or 75%. So it's used a lot in driving the intensity of LEDs, and the other area it's used a lot in is motor control. If you're controlling servo motors, you'll find that that's used for controlling servo motors a lot, so useful to know. So what I have here is a little example. Again, taking the same pin, it's going to set up a pulse, an on-off frequency of 1 hertz, and a duty cycle of 512. So the duty cycle of 512 means it's 50% on, 50% off. Full duty is 1K, 512 is half that, so duty cycle on or off. So again, the same, another way, an alternative way of driving these LEDs. So hopefully, we have some blinking LEDs. Okay, so they should be on for half a second, off for half a second, in this case here. So that's pulse width modulation, and if I just switch that off, that's it. Now, another alternative, so this is just quick, simple demos to show you some of the features internally here and just visualize them with the LEDs. Another way of controlling something is with a timer. So the ESP32 has 4 internal hardware timers on it, and they operate in 2 modes. So you can do a one-shot, so you can basically define a pattern is wait for a certain amount of time, go high, and just trigger something. Or the more frequent one is you have a continuous periodic wave going out, and that's a timer.periodic. So what you do here, let's move this up, is again, I initialize an LED connected to pin 26 as an output. I define a function flash LED, and then I attach a timer to pin 26. So what I have here is I set up I initialize a timer, and then I set it up for a period of 1 second in a continuous mode and have a callback function. So every 1 second, it's going to call back that function that I've written there to flash the LED. So if I right-click that, we should again have our LEDs coming on and off. Okay, so 3 different ways for just driving, just to show the capabilities. The pins are general purpose I/O pins. They can be configured as inputs or outputs. And then behind the scenes, you can attach pulse width modulation, timers, interrupts, a bunch of different things to them. So let me just disable that timer. And the final one to control the pin is set up an interrupt. I really should have brought a mouse with me. Apologies. So again, on this board, I have pin 26 connected to the LED, and I also have a little button on here connected to pin 0. So I'm setting up pin 0 as an input. I define this button interrupt service routine, which is just define this function here, and then I'm going to attach that. I'm going to attach an interrupt to my button. And what it's going to be is on the falling edge of when the button is pressed, it's going to create from a high to low signal. On that falling edge, it's going to call that the interrupt service routine, right? So you can imagine having a sensor picked up, like a gate opening or closing, something like that, or an actuator or something. So if I run this, Okay, nothing's going to happen. But if I press my little button, hopefully you'll see the LEDs toggling every time I press the button. Okay? Now, NeoPixels. These are cool little things. So they're addressable. They're chained together in series, and you can individually address them. They contain an RGB LED in them, and you can then play around with color, and you can do all sorts of patterns because they're individually addressable. And you can buy them in this little lens like this here and string them into huge long lengths once you have enough current to drive them and program. I've seen people doing displays and all sorts of weird, wonderful things out of it. So this particular board comes with a NeoPixel module, which I'm just importing there. I'm defining this ring here. It has 24 LEDs on it. Again, it's connected up to pin 26. So I create this object here, which is a NeoPixel object, what pin it's attached to, and the number of LEDs in that pin. And then I have a simple method here, which is just going to generate a pattern on these here. And it's going to run through that cycle twice. So if I, so very simple. It's just going around the ring. Very simple. It's going to do that 2 times. So nothing sexy. Now, are we on time? Okay. This is something here. This section here, I just thought I'd include it. It's Jupyter Notebook specific. With this particular module, I'm running all the code directly on here, but there may be cases where you may want to have a cell that you're running locally on your laptop, run something there, and then other cells running remotely here. So there's this local this local notion that we can use to do that. So let's have a look at this. So again, on the board, I am going to define a function here called setColor. It's going to take in an RGB, and it's just going to turn these LEDs to that color. And then in this next cell, what I have here is I am going to pull in a widget, a notebook widget. It's just a color picker. So that's going to be running locally here. I can select from the color picker color, and then using this remote keyword, I can then remotely call that function that I've defined on the board here to turn on the LEDs directly. Ooh. Yeah. So running in the cell here, I have my little color picker. So let's go and pick red and click OK. So putting on red onto these, and then if I just pick something like a different color. Yeah. Okay. So nothing fancy, but it's just interesting that you can. I'll turn these off before it annoys you. So it's just interesting being able to run some cells locally here and interact with the remote code here. Okay, so that's a kind of a flying tour over just some of the capability of the general I/O pins. Now, this next section, I'm going to talk about one of the really popular hardware buses that you'll find on these ESP32s. It's called the I2C bus. And it's a 2-wire bus, just has a data line and a clock line. And the typical configuration is you have a master, think your microcontroller, and then you have slave devices. And each of these slave devices is addressable by a unique address. So you'll find that you can buy an awful lot of sensors relatively cheap. $1, $2, $3, maybe temperature sensors, sensors for reading your pulse, blood oxygenation. I have some examples here, or maybe gyros that look for acceleration or angular momentum. Those type of sensors. They're all available, very, very cheap. And the common interface for a lot of those is I2C bus. So It's very popular. It supports up to about over 100 slave devices on the address. They're uniquely addressable. If you have multiple sensors on there with the same address, there's different mechanisms for dealing with that, but I won't go into that. It's generally slowish data rates of the order of maybe 100 to 400 kilobits a second. But for sensor type of information, that's generally sufficient. Okay. So this little cell here, again, we saw when we looked at the modules as an I2C module. And when you're initializing the I2C module, you define what pins the data I2C data pins and clock are connected to. On this board, it's pin 22 and 21. So what I'm going to do here is, this is just a bus scan. It's going to initialize saying, it's going to initialize the I2C bus and then just scan all the addresses from 0 to 128 and see if a device responds to them. So it sends out an address, waits to hear back and acknowledge. And if there's no acknowledge, then there's no device. And if it gets acknowledged, it says there is a device there. And it scanned the bus. It's found one device at hex 76. And I have one device, and it's this device here. It's a small little environmental sensor. It just reads humidity, temperature, and barometric pressure. So again, costs maybe $1 for this device. And if we want to read the details of that sensor, I put a link to this library, this BME280. That's the sensor. I just put a link to the library that I'm using. So I have that on the board here. And if I run this, every couple of seconds, it's just going to come back with the temperature, humidity, and pressure on the device. Okay? So very simple. So now, there's something that's interesting. So what really caught people's attention when these expressive chips came out was the built-in wireless capability at the price point. So as I say, there's two supported wireless standards here. There's Wi-Fi, it's 2.4 gigahertz, and Bluetooth low energy as well on it. So if I just say do a network scan here, so I'm going to import the networks module, set it up as a station, and then I'm just going to scan to see what networks we have here. It's probably going to return a lot. Yeah. Okay. Pardon?
PSNI surveillance.
all for €10, I know. Yeah. Yeah. So now, so I have the. So I know the Python people have kindly given me the credentials to log on here, but what I've done is I have them stored in a JSON file here rather than exposing them to the world. So, I am going to expose them to the world. Let me just comment. Well spotted there, Batman. The hotel will rear up on me. So all I'm going to do here is I'm going to read in this JSON file, just parse out the SSID password, and hopefully we'll be able to connect. And come back with an IP address. You better. No, hang on. Oh, hang on. I think that's the next section. It is the next section. So let's just connect up to the network here. Okay, we do have a network connection. So MicroPython, these are all out-of-the-box libraries with MicroPython networking. This is one of the standard libraries. Now, obviously, it's a cut-down version of the full Python version, but it's enough to get you get these devices connected up to the internet. Now, just show you a simple example here. I'm just going to connect up to an NTP server, Google's NTP server, and then there's a real-time clock on these devices. And and just set the time on it, right? So what I'm doing here is I'm reading the time that's on the clock on the device. Since I powered it on, it'll default back to, I don't know, 1990 or something like that. And then I'll sync it with NTP server, and then it should be the time now. 2000 goes back to, okay. Just one thing to note, the real-time clocks on these things are not the most accurate. So if you're looking at having an application where you want to have accuracy within, a few seconds a month or something, the built-in one is not super accurate. But there are other chips, and I think I put a link. I do mention this DS3231, a cheap device, about $1. But it's a much more accurate real-time clock, and it's got temperature compensation as well, so there's not a huge amount of drift. But if you've got an application where you just want to power the thing down, and you're not concerned about losing a few seconds or a minute a day, the built-in one is fine. Just be mindful it's not super accurate. So since we've got network connectivity, we may as well have a look at some HTTP requests. There is a U requests module, greatly cut down on the Python one, but it does have a reasonable amount of support for what most people would be looking for in a small little device. So let's have a look at its import.
Run Flask on it. Flask?
It's you might be the first. Okay, sorry. So the request library, you can see what functions they have. Get, post, put, patch. I don't see options there, so it's pretty basic, right? But it's enough to do something with. Okay. This next section here, I'm just going to this JSON placeholder one. It's just got a load of JSON up there. I'm going to get some data from there. I'm going to look at going to parse that out, parse out the status code, the reason, and then the body of it, and then convert that body into JSON because it just come back as text. But there's also a standard. There's a JSON library as part of MicroPython as well. So we have a look at it there. Okay, so very simple stuff. Okay. Right, we have 10 minutes left, so I think we're okay. So I mentioned a lot of applications of these would be, you can see here I've got this connected up to a USB cable, all the power's coming over this, but a lot of the applications are, you stick it in a corner, battery powered. And it's a reasonably fast processor, it's got Wi-Fi, so it can be quite power hungry. If you put up a little LiPo battery onto that, it may only last, half a day or something. So the way to get longevity out of that is to put the device into sleep when you don't need it to do anything. A lot of the applications are wake up periodically, do a bit of work, send your data over Wi-Fi or LoRa or whatever it is, go back to sleep. And the ESP32 has a number of sleep mechanisms. There's a light sleep mechanism, and then there's a deep sleep mechanism. And basically what that is, on that block diagram you saw earlier, there's lots of different modules on the chip, and it just decides which ones you're turning off. In the deep sleep, it pretty much turns everything off except for the ultra-low processor, coprocessor. With the light sleep, the memory is still powered on, so you can wake up from that and still have data in state in your memory. Whereas with the deep sleep one, it's effectively like pressing the reset. There are some mechanisms for storing the data so that when you wake back up, you can read them out and then continue on where you left off. And the typical way you wake up from sleep is there's a number of mechanisms. You can set a timer. So set a timer, say, wake me up in 24 hours, and it'll do that. Or you can wake it up on one of these inputs. So you can take one of the input pins, and you can basically, when it's activated, wake the device up. And what I'm doing here is I'm going to, I have two pins wired up here. You can wire them up this way, but one of them, this pin 0 is where I got my button. I'm going to go to sleep, and then when I press the button, it's going to wake back up, okay? So hopefully. So that processor is now in deep sleep mode, and it's going to do absolutely nothing until I press my little button here. And hopefully it'll wake up. And you can see in the first line, it gives you the reason for the reset. It's a reset from a deep sleep mode, okay? Now, so that's pretty much the kind of capability of the device. One thing that's useful to know is some standard tools for transferring files back and forth. The one I prefer is ORShell. Again, just type ORShell, your port number, and you can then do, the board is actually accessed by this /pi board. And the pi board is actually a name of a board that the MicroPython people have themselves. But it doesn't matter that this is a different manufacturer. You can then just copy data back and forth from it. Yeah. And then the other area is if you want an IDE, Visual Studio Code, there is an extension called PyMaker, which is quite useful. And it'll have the built-in REPL, transferring files, and remotely accessing and the code on here. And that's from a Dutch company called PyCon. And they specialize in making industrial boards based off this ESP32 for IoT application. It's worth looking at their website. They got some really interesting stuff there. A lot more expensive than this, but it's quite good capability. Slight aside from the coding side, if you find yourself getting into hardware, you may want to start looking at debugging some hardware. And these here are logic analyzers, believe it or not. The one on the left costs $9 or $10. The one on the right there costs double that. And so they both have 8 channels, about 24 megahertz, so they probably have about a 10 megahertz bandwidth. But so if you're debugging things like the I2 square or the SPI bus, which are hundreds of kilohertz or 1 or 2 megahertz, you have plenty of bandwidth there. And there is a great little tool called Sigrot Pulse View. So what it is you get the inputs, you connect up the wires in those logical analyzers to, in this case, my SPI data, or sorry, my I2C data and clock pin, and you can see the transitions. But it has this notion of decoders. So you can stack decoders and decode this information. So this is the actual electrical signals on this on the I2 square bus. This decoder here will tell you it's a 1 or a 0. And then you can stack another decoder that will tell you that that is an address read at address 59 and it didn't get an acknowledge. So what's been shown here is actually that I2C bus scan. So for the first 3, it goes through address 59, 5A, 5B, and there's no acknowledge, so there's nothing there. And then the very last one you may not be able to see, but there's an A just in here, and that means there's some device is on that address and sends back an acknowledge, and that's how you know the device was there. So if you start getting into these little devices and you're debugging something, there's a good chance it could be a hardware wiring problem as opposed to a code problem. We're all familiar with IDEs and debuggers, but to debug some of the hardware issues, a little cheap logic analyzer and this Pulse View tool is fantastic. Okay, I think that's about all I have for you. I do have some of these devices with me, so we can, if you want to look at them, I'll be out in the hall there for a few minutes and we can have a look at them. Okay.